NCERT exercise solution for chemical kinetics, and we will be doing problem 4.21 to 4.25. So problem 4.21, what they have given, the following data were obtained during the first order thermal decomposition of SO2Cl2. What is SO2Cl2? SOCl2 is sulfonyl chloride. Okay, and the equation is given to you, that is your sulfonyl chloride SO2Cl2 gas is decomposing into SO sulfur dioxide gas and chlorine gas Cl2 gas. Okay, this is the equation. And what other information here we have? They are saying that this thermal decomposition is at constant volume. Okay, at constant volume means what? When volume is constant volume. When volume is constant, we can write down the rate expression in terms of the pressure. Okay, so rate can be given for the same equation. We can write rate as K partial pressure of SO2Cl2 at any time will give you rate of the reaction at that particular time. So this is the rate expression, and we have written rate expression keeping in mind that reaction is taking place at constant volume, therefore partial pressure is used, and this is first order kinetics. Okay, therefore the partial pressure term is having power 1. Now, what we have to calculate in this case, they have given a table. In this table, they have given two experimental observations. One is at time 0 and another one is at 100 second. And at two conditions, they have given the value of total pressure. Okay, the container in which reaction is conducted, in that container, pressure at these two interval of time has been given. What we have to calculate rate of the reaction when the total pressure is 0.65 atmosphere. Okay, now one thing that we have to remember in this case, that is at time 0, whatever total pressure is there, that is initially we will be having only your sulfonyl chloride, only the reactant. Therefore initial pressure, suppose we are taking P0, which is synonymous to the initial amount in case of the concentration term. So this is the first observation, or the first experimental value is nothing but P0. This is the P0 value, initial pressure. Now after some time, when reaction will take place, some amount of this P0 will react. So pressure at a given time or the partial pressure of your sulfonyl chloride will be P0 minus P if P amount of sulfur dioxide and chlorine are produced. Initially these two are 0. They are not there in the medium because only reactants are there. This P0 minus P is nothing but it is A minus X, amount left after some time after when reaction has started. Okay, now at a given time, if we want to know this value, that is A minus X, we can use this term P0 minus P. But at a given time in the reaction, that is the vessel in which we are conducting the reaction, we do not know what is P. Why? Because at a given time, the second observation that they have given at 100 second, here they have given total pressure. So this total pressure, that is P total. Okay, this total pressure is the total pressure of your sulfonyl chloride, that is P0 minus P, plus partial pressure of sulfur dioxide plus partial pressure of chlorine gas produced. So we will be getting here value P0 plus P. Okay, or we can say that P is equal to P total minus P0. Suppose this is our first equation. Okay, now here the known parameters are either P naught or P total, but we do not know what is P. So therefore, we cannot write down A minus X as P naught minus P because we do not know P. So therefore, we will put down the value of this P obtained from equation number 1 to find out P naught minus P. So we will write here P naught minus P can be written as P naught minus P value from equation number 1 is P total minus P naught. Okay, when we will open the bracket, this P naught inside the bracket will become plus. So therefore, we will be having 2P naught minus P total. P total will be negative here. So what we can say, this P naught minus P is equal to 2P naught minus P total. Suppose this is our equation number 2. Now here what we have obtained, we have obtained the value of P naught minus P in terms of known parameter. What are known parameter to us? We know P naught and we know P total. Okay. Now we have to calculate rate of the reaction, and rate is given as rate constant multiplied by partial pressure of your sulfonyl chloride at that very time. So for this, both the quantities should be known to us. We should know what is rate constant and we should know what is the partial pressure of sulfonyl chloride at a given time. So for this, first we have to calculate the rate constant. So rate constant at time is equal to 100. Rate constant can be written as 2.303 divided by your time, which is 100, and log of A by A minus X. Now in our case, what is A and what is A minus X? We will write down the values. Our A is, we can rewrite the same equation as 2.303 divided by 100 log of P naught by 2P naught minus P total. A minus X we will put down from the equation number 2. Okay, this value from equation number 2. And your P naught minus P from equation number 2 is 2P naught minus P total in terms of the known parameters. Okay, now we'll put down the values. So what we have here, it is equal to 2.303 divided by 100 log of, the first value is the P naught. P naught is 0.5 atmosphere. So we write it as 0, just a moment. We write it as 0.5 divided by 2 into 0.5 minus 0.6, because here at 100 second we have P total as 0.6. So we will be getting after simplification, the value of K which we obtained here is 2.23 into 10 raised to the power minus 3 per second. This we will get after doing calculation from here. So this is the value of K obtained. Okay, now we know the value of K obtained. Second part of the question, what they are saying, calculate the rate of the reaction when total pressure is 0.65 atmosphere. So we note the rate expression, therefore we will write down when your total pressure is equal to 0.65 atmosphere. Okay, so here at this time we should know the partial pressure of SO2Cl2, which is equal to P naught minus P, and this is equal to 2P naught minus P total. Okay, so therefore we will put down the value here for the quantities, and 2P naught is 2 into 0.5 minus P total is given in this case is 0.65. So we are getting here the value as 0.35 atmosphere. This is partial pressure of SO2 Cl2 at this moment. Okay. Now next what we have to calculate? We have to calculate rate. So rate can be calculated as what will be the value of rate? K partial pressure of SO2 Cl2, which is equal to rate constant value we have calculated as 2.23 into 10 raised to the power minus 3 per second into 0.35 atmosphere. Fine. So the value of rate we'll be getting from here is 7.8 into 10 raised to the power of minus 5 atmosphere per second. This is our answer. Okay. Now come to the next one, 4.22. What they have given in this question, the rate constant for the decomposition of N2O5 at various temperature is given below. They have given a table. In this table, they have given different temperature value and they have given the value of rate constant in the second row, and what we have to do, draw a graph between ln k or natural log of k and 1 by t and calculate the value of A and EA. That is, A is the pre-exponential factor and EA is energy of activation. And one more thing, predict the rate constant at 30 degree and 50 degrees Celsius. Now in this question there are three things to do. So the very first one that we have to do, first one is to draw a graph between natural log of k and 1 by t, and for this we will be writing the given data again because we will convert the given data in the form we will require for the plotting the graph. Okay, the very first part of your problem is you have to draw a graph between natural log of k and 1 by t. So what have a look here, what they have given. They have given temperature values and these temperature values are given in degrees Celsius. So because we will be plotting in what you call standard unit, so therefore we'll convert in Kelvin. So we will be converting temperature in degrees Celsius into Kelvin, like 0 degrees Celsius will become what? 0 degrees Celsius will become 273 Kelvin, as you know how to convert. And the second value is they have for plotting the graph we need 1 by t. So therefore this temperature we will find inverse of it, that is 1 by t will be per Kelvin and the values we will calculate out. After that the value of k which are provided to you, we will take natural log of all these values and we will get the third set of values where we have natural log of k for plotting the graph. Okay, so we are doing the first part of the problem, that is draw a graph between natural log of k and 1 by t, this part. So have a look here, graph we have already plotted, graph of natural log of k and 1 by t. We have taken 1 by t on x-axis, and since values are given as 0.003663, so we will write them in the standard form. Therefore, we will put down here 1 by t into 10 raised to the power minus 3 per Kelvin to write down the numbers in a standard form. And natural log of k we have taken on the y-axis. Since the values of ln k are the negative values, therefore we are starting the values from minus 15 as we have here, and we will go till 0 upward, and for the values of 1 by t we have taken the standard form of them, so therefore values are starting from 2.8 to 3.8 in the scale. And from this plot we are getting 4 points, one here, one here, from the data given, another one here, another one here, and one here. So these are the 5 points obtained, and accordingly we will be getting a straight line. Sometimes the points you located, they do not fall exactly on the straight line. It's okay, it will not make any difference. We have some errors sometimes in experiment as well as while plotting the graph. Okay, so what we have to do here, we have to this is the plot, and from the plot now we can find out the things from the slope that we are getting. What they are asking us, calculate the value of A and EA, that is energy of activation. So we will try to find out with the help of the plot that we have here. First we can find out the slope of this plot. Okay, and slope of this plot will be, as in any case, slope can be of any straight line plot can be given as y2 minus y1, that is final observation on y-axis minus initial observation that we are taking on the y-axis, divided by x2 minus x1. Okay, in our case we are taking the final value on the y-axis. This is this value for minus 14.055. So we will write it as minus 14.055 minus initial value, that is we can find out a slope in between any two values. Like for example, we are plotting slope in this case like this. So in these two values, so here initial value is this one and final value is suppose this one. So minus 10.98. This is how we will be having the plot, sorry. Okay, so divided by x2 minus x1. x2 in our case is 3.663 minus 413 here in this case, and we will write outside this into 10 raised to the power minus 3, the scale which we have chosen, and it is in per Kelvin. Yeah. So we will getting the value of slope here as after simplification we are getting minus 3.073 divided by 0.25 into 10 raised to the power minus 3 per Kelvin. We are not simplifying, we will use this value of slope later on in our calculation. So this is the value of slope. Fine. Now come to the question. We have to find out the value of energy of activation, and we have to find out the value of A, which is pre-exponential factor. So for this, first we will be writing the Arrhenius equation. You know what is Arrhenius equation? Arrhenius equation is rate constant can be calculated in terms of this A, which is pre-exponential factor, and we are having a power of exponent as or exponent is raised to the power EA upon RT, where E is energy of activation, T is temperature, and R is the gas constant. If we take natural log of this equation, the same equation can be written as natural log of K is equal to natural log of A minus EA divided by R dot 1 by T. We can write it this way. Suppose this is equation number 1. Okay. This equation is the equation for any straight line graph, and what we have here y is equal to mx. This is m dot x, and this is plus c. Okay, so in our case on y-axis we have plotted ln k here, and on x-axis we have plotted 1 by t here. So from this what we are getting, from the slope what we will get, from the slope which is m, we will get energy of activation. Okay, so we will write here slope is equal to minus, because negative sign is there, EA upon R, or energy of activation is equal to your what we have, we multiply minus slope into R. Okay, now we have calculated slope here. Fine, so we write down the value of slope down here. This is equal to minus 3.073 divided by 0.25 into 10 raised to the power minus 3 per Kelvin, multiplied by the value of R, which is 8.314 joules per Kelvin per mole. Okay, the what we have here, minus out here, and the Kelvin per Kelvin here. So what we are getting on simplification, we are getting the value of energy of activation, as it will be positive value, minus will become plus, so it will be 102195.7 joules per mole, because per Kelvin will cancel out. So what is the final value? EA, energy of activation, is written as 102.195 kilojoules per mole. This is our first answer. They were asking us to calculate energy of activation. Okay, this is our first answer. Now second part, that we have to calculate the pre-exponential factor also, that is A is the pre-exponential factor. So how to calculate A? We will write down the previous equation, that is equation number 1. Yeah, equation number 1 can be rewritten as your natural log of pre-exponential factor is equal to EA upon RT plus natural log of K. We have rearranged equation number 1. So what we have here, how can we find out the value of ln A? At temperature is equal to 273 Kelvin. Okay, what is the value of natural log of K? I'll show you in the table that we have made, minus 14.055 at 273 Kelvin. Have a look here. At 273 Kelvin, value of your natural log is this, minus 14.055. So we will be using this value here to calculate our pre-exponential factor. Therefore, natural log of A is equal to energy of activation. We have already calculated. So it is 102.20 kilojoule per mole divided by what we have in the end, 8.314 into 10 raised to the power. Here we are writing this in minus 3 because your value here we have taken in kilojoules. Okay, so here its unit will be now kilojoule per Kelvin per mole. Okay, into 273 Kelvin temperature. So minus, we will be writing down the value 14.055. Here we will be getting value after simplification. Your value will come as 30.0 973 as the value of ln A. We will take anti-log. So after taking anti-log, A will be calculated as 2.83 into 10 raised to the power 13. This is the value of your A. That is our first answer. Sorry, second answer. Our first answer is this one, value of energy of activation, and this is our second answer. Okay, so from here to here we will do after taking anti-log from the anti-log table. Now third part of our problem, we are left with one more. What is this? Predict the rate constant at 30 degrees Celsius and 50 degrees Celsius temperature. Okay, 30 and 50 degrees Celsius. Fine. So for this, what we have, we will be taking help of your graph for this. So value of rate constant. Okay, that is K at two different temperature. What are the values of rate constant? Values of rate constant at two different temperature. At T is equal to 30 degree, which is given in our question. 30 degrees Celsius temperature means 303 Kelvin. And when we make 1 by T of it, it will be 1 by T will be 0.003300. Okay, after calculation. So we'll be writing it as 3.3 into 10 raised to the power minus 3 as the value of 1 by T. Okay, now we will find out the value of natural log of K, and this natural log of K we will calculate from graph. Okay, so at 3.3 natural log of K, have a look in the plot. At 3.3, this is 3.2, this is 3.3. At 3.3 we will find out the natural log of K here. Value will be somewhere here. Okay, so this value is closer to 9. Therefore the exact value is ln K is equal to minus 9.7. So we will take anti-log, and after taking anti-log, value of K we are getting as 6.13 into 10 raised to the power minus 5 per second. And this is our first value of K at 30 degrees Celsius temperature. Now at a temperature is equal to 50 degrees Celsius, that is 323 Kelvin. Okay, so here we will find out 1 by T in the same manner. 1 by T will be 0.00309, which is equal to 3.090 into 10 raised to the power minus 3. This is the value of 1 by T. At this value of 1 by T, that is 3.090. Have a look in the plot what we have. 3.090, that is 3 around 3 roughly. So what is the value of K? So this is the value. It is closer to 6. Yeah, it is here, it is falling here, so it is around 6, slightly more than 6. The value will be accurately ln K from the graph will be equal to minus 6.3. And when we take natural log of this, we will take K value as 1.84 into 10 raised to the power minus 5 per second. This is our second answer. Okay, Sorry, this is 3, not 5. This value is 3. First one is power 5, second one is 3. So this is our first answer. This is our second answer. The rate constant at 2 temperature which are given to us. This is all about this problem. Come to the next one. Constant for the decomposition of hydrocarbon is given at 546 Kelvin, and they have given the value of energy of activation also, and we have to find out the value of pre-exponential factor. First we will write down what information they have given to us. They have given the value of rate constant which is equal to 2.418 into 10 raised to the power minus 5 per second, and they have given the value of energy of activation also, which is equal to 179.9 kilojoules per mole. And we have to find out pre-exponential factor. In Arrhenius equation, constant A is called as pre-exponential factor. We have to find it, and they have given temperature for the rate constant as 546 Kelvin. Okay, so what is this A and how we are going to calculate? So according to Arrhenius equation, we have rate constant is equal to rate constant is equal to A, that is pre-exponential factor, E minus EA over RT, where EA is the energy of activation, R is gas constant, and T is the temperature. So if we take log to the base 10 of the whole equation, the same equation can be written as log K is equal to log A minus EA divided by 2.303 RT. Okay. Now, we have to find out log A. So therefore, we will rearrange the equation. So log A is equal to log K plus EA divided by 2.303 RT. Okay, now we will put down the values. Log K, log of value of K is given to us. So K is 2.418 into 10 raised to the power minus 5 plus EA is given as 179.9 kilojoules. So therefore we are multiplying by 3, and unit we will write joules per mole divided by 2.303 and multiplied by value of R, that is gas constant, 8.314 joules per Kelvin per mole into 546 Kelvin. Okay, so the values, you can find out the unit also. Per mole, Kelvin can cancel out, joule will cancel out. So what we are getting here, after taking log of this value, we'll take log of this value from the log table, and the value we are getting as minus 5, because there is a negative power to the base 10. So minus 5 plus 0.3834 and plus we are having we have to simplify the second expression, this one, and after simplification we are getting value 17.2081. This is calculated as 12.5915 per second. This is the value of log A. So A will be taken as anti-log of 12.5915, and we are getting value as 3.904 into 10 raised to the power 12 per second. Okay, so this is the value of A that we have to calculate. That is the value of pre-exponential factor. This is your answer. Now 4.24. In this question, consider a reaction A giving product with K value. Calculate concentration of A remaining after 100 seconds if initial concentration of A is 1 moles per liter. So the informations which are giving to us, first we'll write down the equation. Any reactant A is converting into product. And for this, rate constant value is given as 2.0 into 10 raised to the power minus 2 per second. And what they are asking, they have given the initial concentration, that is A naught. This A naught is equal to 1.0 moles per liter. We want to find out concentration of this at a particular time. That is what they are asking. Concentration of A remaining after time is equal to 100 second. Okay, so we will be using, since it is from the equation, this will follow the first order kinetics. So we are writing K is equal to 2.303 divided by T log of A naught divided by A, initial concentration divided by concentration at a given time. We will simplify this, that is the terms with the log term we will keep on one side and other parameters we will have on other side. So what we have, K into T divided by 2.303 is equal to log of A naught minus log of A. Okay, now we will put down the values. And we have to calculate here log A. So therefore log of A is equal to log of A naught. Okay, and this term that is on right hand side, this is negative term, so this will be positive on left hand side, while this term when we bring on right hand side it will be negative. So here we'll have minus K into T divided by 2.303. So therefore we'll put down the values. Log A is equal to log A naught value. A naught is given as 1, so log 1 minus K value is given as 2.0 into 10 raised to the power minus 2 per second into time given as 100 second divided by 2.303. So this is equal to log 1 is 0 minus 0.8684 is the value of log A. So if we want to find out the value of A, it will be anti-log of this. Anti-log of minus 0.8684. So we will be getting value of A from the anti-log table as 0.1354 moles per liter. This is our answer, that is concentration of this substance after 100 seconds will be this value. This is your answer. Come to the problem 4.25. Here they have given sucrose decomposes in an acid solution into glucose and fructose. So the equation that they have given here as sucrose is undergoing decomposition and it is converting into glucose and fructose. And for this T half is given. T half is given as 3 hours. Okay. And what we have to calculate, what fraction of sample of sucrose remain after 8 hours. Okay, after 8 hours, and we have to find out the fraction. So what we have, the initial amount of any substance, that is sucrose, will be taken. If suppose it is taken as A naught, initially we will be having concentration of glucose and fructose 0, and at a given time concentration of sucrose will be A. Okay, that is after 8 hours. They have given 8 hours, so fraction after 8 hours we have to calculate fraction of sucrose. Fraction of anything is what? It will be the quantity which is left divided by the original quantity. This will give you the fraction, and we have to calculate this value after 8 hours. Okay, for calculating this, the very first thing that we should know is the rate constant. Okay, so rate constant for first order reaction will be calculated as 0.693 divided by T half. So this will be equal to 0.693 divided by T half is given as 3 hours. So therefore value of K will be 0.231 per hour. This is the value of K, or the rate constant. Now we will use this equation for the first order kinetics, that is time taken is equal to 2.303 divided by K log of A naught over A, initial concentration divided by concentration at a given time. Now we will rearrange this equation, and we will bring the terms, log terms on one side and other on the other, left hand side. So what we have, K into T divided by 2.303 is equal to log of A naught over A. Now we will put down the values. So log of A naught over A is equal to value of K, which is 0.231 per hour, into time is 8 hours, and divided by 2.303. This R will cancel out. So we are having value as 0.8024. This is the value of log A naught over A. Now your A naught over A will be equal to NT log of this value, that is 0.8024. Okay, and after taking NT log, we are getting value as 6.345. Now we have to find out A upon A naught. So therefore where A upon A naught will be equal to 1 by 6.345. This is equal to 0.158, and this is the value of the fraction of sucrose. Okay, so this is your answer. This is the fraction of sucrose after 8 hours.